Physics 1 video labs, or virtual labs, or do-it-at-home labs, whatever you want to call it. Today's lab, I want to discuss kinematics on a ramp. This is, equipment-wise, a fairly straightforward lab. I, in fact, have all the equipment sitting right over here, or almost all of it. So let's move the camera. We're in the modern physics lab today, because the other lab is being used for something else at the moment. So that's why everything is unfamiliar. In case, equipment-wise, what you need are two marbles right here. Really, this is not two marbles, it's a marble and a steel ball bearing. The point of this is that these two are the same basic size, but they have different densities, and therefore they have different masses. In principle, you don't have to have two objects of the same size, but I wanted to control as many variables as I could. So you have a marble and you have a steel ball bearing that's the same size as the marble. Okay. Second piece of equipment that you need is something to make the ramp out of. What I have is this little, I think they're called U-brackets. If you look at it from the side or from the edge, you see it has kind of like a U shape to it. I got this from Lowe's, as it turns out. You should probably be able to find it at most hardware stores. And then, in addition to that, you need some sort of a protractor. So this right here is an adequate protractor. You need to mark on the ramp a point on the end to start from and a point in the middle to start from. And so you'll need either a tape measure or a ruler in order to make those marks on it, but you won't really need the ruler thereafter. Or a meter stick works as well. And in fact, I have the meter stick right here that I used for this. The thing is, you want this ramp to be at least 1.2 meters long. Okay, so for comparison, that's about 4 feet. So if you go to Lowe's, for example, you can find these as a 4-foot long ramp. So it's 4 feet long is a little more than 1.2 meters. Actually, this red mark here, I think, is right at the 1.2 meter mark. Okay, so equipment-wise, you need that. You need maybe something to elevate the ramp so that it's actually a ramp. For that, just a textbook is probably adequate, or something equivalent. I'm reticent to use any of the equipment in here, but something like this spool of string is actually probably adequate for one of the angles that we need. The instructions actually tell you some very specific angles that you'll be wanting to use. I'm not going to walk through all the theory work, but you're supposed to use a 2-degree angle and a 4-degree angle. For what it's worth, a 2-degree angle, I think I state in here, yeah, in your instructions, that you need about 1.7 to 1.8 centimeters of rise for every 50 centimeters of length. Okay, so you can do this, you can measure this one of two ways. You can use your protractor, and if you do that, you place the protractor down here near the edge of the ramp, and then you move it so that the ramp sort of touches your little crosshair area on the protractor. And I'll try to draw a blow up of this on the board. Okay, and then you basically move the ramp, or move the end of the ramp so that it crosses the 2-degree mark, which, as it turns out, it does right now. Okay, so that's option 1. Option 2, if you know the length of your ramp, you can measure the height and then use the fact that the sine of this angle is that height divided by the length of the ramp at which you've measured the height. Alright, so the basic idea here is that we want to look at what the acceleration is for the ball going down the ramp. And we want to show or see whether it is a constant acceleration. So what we do is we select a stopwatch function on my phone, which is what I'm going to be using as the timer. So I've got my stopwatch ready. I place the ball. Recall that I've marked the ramp here at the midway point. So I place the ball there, and then simultaneously I need to release the ball and hit the timer and basically just time how long it takes to go down the ramp. And so we're going to reorient the camera a little bit so that we can see. The ball is right here. Oops, off the stopwatch. And what we do is we say ready and go. At the bottom of the ramp, we stop. And it turns out that I got some time. And so I basically record that time in a table. But you basically write that number down in the trial 1 part of the table. Then you repeat for 5 total trials. And then you repeat using the same ball at the full length. So same ball at full length means we come up here where I've marked off the full length. So start at the top, start the timer, stop the timer, and I've got some time on my stopwatch. Okay, and so that goes down into the next row on my data table, the full length row, trial 1. I again do multiple trials, 5 trials of this. Once I've got those 5 trials, I can either go on to the statistics part of it or go back and continue the experiment. So I'm going to go ahead and continue the experiment while I can. So this is part 2 experimental stuff. The first row of data is just the same data that we just took, because it is literally a repeat of what we just did in the first part. So you do not have to repeat the data. You can just copy it. Top row of part 1, you can copy to here. And now we're going to repeat it, but with a bigger mass. So this is my bigger mass. What I do is I put it here at the midway point again, and then once again I release and start the timer, and then when it gets to the bottom I stop the timer and basically record what is my data. And then the last thing you're supposed to do, data collection wise, is see what happens if you go from a 2-degree angle to a 4-degree angle. This one right here is now 4 degrees. Okay, so now what I do, now that I've set it up, is I again place my marble on my little marker. I let it roll down the ramp. I time it as it rolls down the ramp. I get some amount of time. That one goes down into this bottom row of data on our table. So we do 5 trials there. All right, once you've done that, your data collection is complete. The rest of what's to do involves some statistics. First item on the equipment notes is that the ramp does not have to be this. You do not have to use this U bracket. There are many options for what you can do to use a ramp. I have chosen this because it was available to me. It was easy for me to find. I think it costs like $10 or something like that, maybe even a little less. For what it's worth, this is meant for 1/2 inch plywood. So basically your plywood piece would slide into this area. If you get larger than this, then the ball maybe will fit entirely in the channel. If you get a little smaller than this, then the ball maybe will be a little more outside the channel. But what's nice about it is that the ball, the marble, I should say, tends to stay on the track. It tends not to fall off the track. But you can use something other than this U panel. If you have something else that you'd rather use, go for it. The only specifications are you have to be able to adjust the angle of the ramp, and the ramp has to be at least 1.2 meters long, or at least, in other words, about 4 feet long. So if you have a board that you want to use, go for it. With that said, one thing that you need is for whatever your ramp is to be smooth when laid flat. A board will work. However, you have to be very careful in selecting your ramp in the sense that it needs to be able to lie flat. So if I take this board and I set it on a table over here, just set it on a table. We can point the camera at the board. Okay. And you can see that this is not level. I mean, I can slide my finger under here. There's nothing really under the board. I guess there's this piece of paper, but if the piece of paper is not doing much. If I move this over here, this board is not by any stretch level. If I set a marble on it, while it's supposedly lying flat, it's going to roll off towards the camera because it's not level. It's very twisted. Let's see if I can set up the camera so we can look down this board. If I hold it straight to the camera, you can see that this is not a very straight board. So this would not be very good as a choice in ramp. It's twisted. Sometimes they are bent. This one right here is another board. Laying it flat down. It's another example of not a good ramp. Reason being that it's bowed. It makes good contact right here. Right here, it's in contact with the table. It makes contact with the table also on the other end. I'm not going to zoom in to show you that. I am, however, going to show you that I can basically put my finger under it and run it. And if I adjust the camera so that it's looking a little more straight on at the board, maybe you can see that there's a gap right here that you can easily move a piece of paper, this far. So it is not a very straight board. So this is, again, an example of what not to use. So my point is, be sure that whatever you've chosen, be it a board, be it a U-channel, be it a pipe, and yes, you could use a PVC pipe, would work. Whatever you've chosen needs to be straight or level when you lie it on the ground, the floor. So that's the major criterion. The material chosen could be anything from a U-channel to a board to a PVC pipe to, you could use your dining table or your kitchen table as long as it's not a folding table. And then prop a book or something under one end of it to make the inclined plane. Okay. So that's it for the equipment. The rest is straightforward. The marbles, we have their, I think they're 5/8 inch. If you use a U-channel, then the diameter of the marble will matter quite a bit. But if you use something flat like a table or a board, then the diameter shouldn't really matter. It should actually have, the acceleration should be independent of the diameter. Right, so now you've seen how to do the lab, but it remains to show you how to do all the calculations for the lab. I'm not going to do literally all of them for you, but I'm going to show you enough that you can get them done. Basically by showing you how to essentially fill out the rest of this table from my data. It's worth stating before I do that my data and your data are not going to necessarily look alike, so don't just copy my answers. If you use the same marbles that I give you for lab, they may be slightly different than the marbles that I use, so your data may be slightly off. The other thing is that if you decide to use a flat table, like if you use your kitchen table instead of the U-track, or if you use the pipe instead of the U-track, you're also going to get slightly different answers. So please don't just go copying my work. However, the process should be very similar. But before we can go on to these calculations, we need a word from our sponsor. Today's video is sponsored by this stuff. This is Grandma's Molasses Unsulfured, original gold standard. And I like to add it to my tea because it kind of sweetens the tea a little bit. This tea needs something to sweeten it. So we'll just add a little bit of molasses and we'll drink some of it.
That is very delicious. So try some of Grandma's molasses today. Right, so to continue with our lab calculations, basically everything you're supposed to do is sort of outlined step by step in this handout, tells you which equation number you're looking at for each step and so on. But still, I'm going to work through sort of a walkthrough with my data. The first thing that you're doing is calculating the mean. So this right here uh, goes into this spot on your table. The equation that goes with mean is listed up here. It's actually equation number 6. So this is to find the mean time. Equation 6 basically says take all the trials, all the times from each trial, add them together, divide by the number of trials. In this case, there are 5 trials. So what we do is let's actually pull open the workspace to do this in. So you have 5 trials. The 5 trials have a value of T1 of 2.85 seconds, T2 of 2.90 seconds, T3 of 2.76 seconds, T4 of 2.99 seconds, and T5 of 2.72 seconds. Okay, I just wrote these, copied them from your table. To find the average time, what we do is we add them all together. So it's 1 over n sum. I'm going to actually change it to j equals 1 to n of t sub j's. Okay, so this basically, you look at how many there are. There's n equals 5 of them. This is T1, this is TJ equals 1, TJ equals 2, TJ equals 3, etc. So what you end up with is 1/5 of 2.85 plus 2.90 plus 2.76 plus 2.99 plus 2.72 seconds. And when you add all those together and divide by 5, you should get something like 2.844 seconds. Okay, and since each of these is actually to the nearest hundredths place, that means that we should probably retain this to the nearest hundredths place when we record it in the table. So if I pop the table open here, basically I'd say 2.84 as the value here. All right. Now, coming back to this, the next question, is to calculate the standard deviation using equation 7. Equation 7 says standard deviation is given by the square root of 1 over n, sum from I or j equals 1 to n ti or j minus t average quantity squared. Okay, so what that looks like practically here is that our sigma, let's just write this out here, sigma is square root 1 over n sum from j equals 1 to n t sub j minus t average quantity squared. Okay, so let's just focus on this part first so that I don't have to carry the square root and all that. So sum from j equals 1 to 5 of t sub j minus t average quantity squared. Basically what this means is that we are doing 2.85 minus 2.844 squared. These are all in seconds, so if you square it, you'd get seconds squared. So that plus 2.90 minus 2.854, excuse me, 2.844, and then 2.76 minus 2.844, and then 2.99 minus 2.844, and then finally 2.72 minus 2.844. All right. Now, order of operations here basically means you take the difference, then you square it, and so you find the difference first, then you square each number, then you add them all together. That's your order of operations here. If you follow that order of operations, what you end up getting for all of these is, well, let's see, this one right here would be like 0.06 or something like that. So add them all together, take square them and all that. Follow the order of operations. What you end up getting here is 0.05865 seconds squared. Okay, and so that number right there is what goes in to this for that right there. So sigma should equal square root 1 over 5 times 0.05865 seconds squared. All right, and so that gives us about 0.108305125 seconds. And again, we should retain out to the hundredths place, which would be this one. So when I go to write that down in my data table, what I'm actually going to put here is 0.11. Oops. Okay. So we've just completed these two steps. Now this step and these sets of steps, these three steps, are the next part, have to do with basically duplicating this work but for acceleration. And there's really three ways you could go about doing this, and I guess just for completeness I'll list them. Okay, and we're actually going to do one of these options. So option one would be basically compute the average acceleration, so this would be a average, and use equation 3. This asks you to use equation 3 here, so we scroll up, look up equation 3. It's the one that says that x is equal to 1/2 at squared, or delta x is 1/2 at squared, this equation. Okay, so you'd solve it for a. Okay, and so what that ends up giving you is that a is equal to 2 times delta x divided by t average squared. Okay, and then you get a small, which is actually equal to 2 delta x divided by t average plus sigma t, which is the standard deviation we just counted, that calculated, that 0.11 second number, and then a large, and that is 2 delta x divided by t average plus minus sigma t squared. Okay. Then to get the uncertainty sigma a, we'd say something like sigma a is equal to 1/2 of a large minus a small. Okay. Where's the delta x come from, by the way? This right here is the distance traveled by the marble or the steel ball bearing. So in the case of my ramp, delta x is 0.6 meters for the half ramp and 1.2 meters for the full ramp. Okay, so this right here is what we're going to actually do. It's actually arguably the least good way of doing this, but it is maybe the fastest way that is purely algebra based. Okay. Option number 2 for how you could go about doing this is you could use you use a sub j, all of the a's are 2 delta x over t sub j squared, and then from there you get the average by literally computing an average. So you'd use this just like we did for the time, and then from there you would use the standard deviation for a is equal to square root 1 over n from j equals 1 to n of a sub j minus a average squared. Okay, so this is like the second way that you could compute this number, and for that matter this number. Third way to do it, and by the way, this second way is probably the most thorough, but it's also the most time intensive in some ways, especially if you have a large set of data. We only have 5 data points, so this one's only slightly more time intensive than this one. The third way is actually better than what we're going to do. It's not as thorough as this, but it's also not as time intensive either. It's called propagation of errors. And this is the way that is commonly used. And however, we're not doing it in this lab because this is not only a physics with calculus lab. In other words, if everybody in the lab was doing physics with calculus and I could expect everybody to do some calculus, this is the method that I would actually prefer to use. But because the general physics people, the algebra-based physics folks have effectively the same lab, since they're all combined into Physics 1 labs, I can't really fairly expect this of everybody. But the basic method is that you take a derivative, you differentiate a with respect to t. So you'd use essentially something like sigma sub a is approximately the differential dA by dt evaluated at t equals the average value times sigma t. Okay, and so what you'd end up getting from this is sigma a is actually 4 delta x over t, just t average quantity cubed times sigma t. Okay, so this is like the way that we would normally do it, because this computation, if you know how to do derivatives, is not especially complicated, especially for an equation of this form. But at the same time, it does take doing a little bit of calculus, and so it's not expected. Okay, and so the compromise is that we end up defaulting to this method right here. Okay, so this is the process that we're going to be doing, and it's done basically in 4 steps in your handout. Step 1, compute the average for the acceleration, which number goes into your table. Step 2, compute this value. Step 3, compute this value. These two are intermediate steps. Step 4, compute this value, which also goes into your table. Okay, so with that in mind, let's see how this step plays out. So first, compute the average acceleration. And that average acceleration, again, is given by 2, is approximately given by 2 delta x over your average time. Okay, so again, for my ramp, that would be 2 times 0.600 meters divided by the average time, which was 2.844 seconds, and that quantity must be squared. Okay, so if we do that, the answer that we end up getting for that average ends up being 0.148, so 0.148, and then it's like 361,789 meters per second squared. And remember that we are only retaining, based on what we have here, this one's actually 3 significant figures, so we can retain 3 significant figures for our table down here. Okay, so we've just done this step right here, and we can write the answer right here, 0.148. All right, so now to do this step, or to get this point, we have to do this step, and this step all together. So once we've done those 3 steps, then basically we are done with this table in a sense, and we're ready to just go make some comparisons. Okay, so now we do a small. Okay, and the smallest should be 2 delta x divided by t average plus sigma t, quantity squared. Okay, so that's 2 times 0.600 meters divided by, and then t average was 2.844 seconds, plus our standard deviation was 0.108 seconds. Okay, and I'm actually going to retain all the digits that I calculated for this guy. There's some additional digits beyond this 8. So I put it into my calculator, and what I come up with is 0.139970769 meters per second squared. I'm not actually recording this in my table, but if I was, I'd need to round it to there. So it'd be like 0.140. Okay, and then similarly we do for a large, and that one is 2 delta x over t average minus sigma t, 0.600 meters times 2.844 seconds minus 0.108 blah 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 seconds squared, and that gives me about 0.160341496 meters per second squared. Again, we take these three digits if we were going to write it in, but again, I can just use the whole thing. Okay, and so now to get sigma A, what we do is we take half of the difference between these two, A large minus A small. So this is half of 0.160 minus 0.1399 meters per second squared, and so therefore sigma A comes out to 0.01, as it turns out, 0.010185363 meters per second squared. Okay, and so basically again we would retain to here, and so on our table right here we would put 0.010 as our standard deviation. Whoops, also got to go here, 0.1010. Okay, this of course all I've done is just copy the above because it's the same as these data. All right, so in principle I'm supposed to do that also for the full length. So if I do that, I get 4.00, I get 0.11 again, and I get 0.150, and I get 0.0 so it's 0.008, so 0.01 no, sorry, 0.00825. Okay, so that knocks out this part. All right, the last thing that you end up having to do is comparisons between these two data sets, and everything that you're doing down here in part 2 is essentially repetition of the steps that I just did, comparison, and then the only other thing is it asks you what's the approximate ratio, which you basically just say these two look like about the same number, so 1 to 1. Okay, so how do you do this comparison? Well, it asks you this question: to what confidence level is there a difference? All right, so this is getting into the theory part 2 stuff, statistics and data analysis. We've made it up through this part of the statistics and data analysis. Now we're making use of our bill curve, our normal distribution, our Gaussian distribution, standard normal curve, however you want to call it. And the full process basically is this. First, we got to get the means and the standard deviations, which is what we just did. That was what we were filling that table in with. And then our next step is to compute a z-score. The z-score, you basically take the larger value, larger value of the averages, the larger mean, and you subtract the smaller mean from it, and then you divide that difference by the sum of the two standard deviations. That gives you a z-score, which you can then look up in a table in the appendix, and then from there you get a confidence level. Okay, so let's do the z-score next. Okay, so what we do is we clear all this out. What we want is the z-score. So z in this case would be, you could call it like a half minus a full, these two averages. And you can, if you don't know from looking which one is greater, which one's less, your actual z-score, you're basically just taking a absolute value of everything that you get. These two numbers down here should be positive anyway, but in principle you take the absolute value of everything. So this would be sigma a half and sigma a full. All right, so what we do is we take those calculated numbers that we have put into our table. So this right here would represent the average for half. This one right here would be the average for full. So we're subtracting these two from each other. These are the two standard deviations in the denominator. So we're adding these two, we're subtracting these two, we're dividing the difference by the sum. Now let's pull this guy back up. You'll recall that I basically said that I am retaining more than my significant figures to complete the calculation. Basically, this difference right here ends up yielding only about one significant figure. No matter how you slice it, it's basically one significant figure worth. So if we keep track of significant figures in that way, what we end up getting is, so on top you end up with like 0.002 meters per second squared. This is, in other words, 0.148 minus 0.150. And then on bottom we have 0.018 meters per second squared. That comes from the 0.010 meter per second squared plus the 0.008 meters per second squared. Okay, so this is 2/9, or in other words 0.1111 repeating. There's no units to this number. For what it's worth, if you kept all the other digits on these, what you'd end up getting is 0.080701619. Now with that said, my result ended up having only one significant figure because of this right here. You only have one significant figure to work with. So either way, what you end up getting is z is equal to 0.1. Okay. Now what do we do with this? All right. So basically what we've just done is this step right here, determine the z-score. So the next step says look up population fraction p in z-chart. That's actually down here in the appendix. Here is your z-chart or z-table, z-score table for a Gaussian distribution, however you want to call it. Now, depending upon which of those numbers you actually rounded to sort of determines which of these numbers we actually would make use of. And I'm actually going to copy this chart. I'm going to paste it in here. We're going to assume that you've kept track of significant figures properly so that this right here is the value. With that said, I'm going to go ahead and say, what if we considered 0.11 and what if we considered 0.08, just to give you two more examples. Okay, but remember the one that's actually correct has the one significant figure. It's just z equals 0.1. Okay, so let's paste this table right here. That allows me to work with it. I'm going to start with the z equals 0.11. All right, and what I'm going to do here, I'm gonna say, suppose that we want to find that. I know I've already circled it a bunch. I'm going to circle it one more time in this kind of blue color so that it stands out a little more. The way you read this Z table is these column labels, or these row labels, I guess I should say, this column of row labels basically is telling you the first two digits of Z. So your first two digits of Z are 0.1. So that means that we look right here. Okay, so we're looking somewhere in this row. Now, this row of column labels is telling you your third digit for Z. Okay, Z equals 0.1 is the same as 0.1 plus 0.00. Okay, so that means that we have to look in this column. We add this to this, we get 0.1. And when we look in this row in this column, we come up with this number right here. All right, so we end up with P is equal to 0.0398. All right, I'm going to box that number because it's the one that we're actually going to use to finish the problem. But for the sake of argument, what if we picked one of these other two numbers? What if we hadn't rounded correctly or whatever and we come up with one of these? So if you end up with this one right here, 0.11, you'd again go to this column, the 0.1 column, but now you'd have to look in plus 0.01. Okay, so this is 0.1 plus 0.01. All right, and so that row and that column meet to give us this number. And so we would have P is equal to 0.0438. And so we'd use this number instead. And then last but not least, what if we had instead come up with this one? I don't know if that color is going to stand out very well. Let's try this. What if we had come up with this number right here? Okay, so this number is 0.0 plus 0.08. So actually we end up looking in this topmost row instead, and we come all the way over here to this column, and so it's this number right here that we'd use. You'd end up with P is equal to 0.0319. Okay, so of those, this one right here is the actual one that we're going to be using. So let's select that. We have just now completed this step right here. Look up population P in the Z chart. So these numbers that I've written down, 0.0398, for that matter, 0.0438, 0.0319, whichever of those you've picked, that is your population value P. That is the value which is bounded. It's equivalent to the value that is bounded between the mean and 0.1 or 0.11 or 0.08 standard deviations from the mean. Okay, so P is this. Your confidence level is always going to be 2 times P times 100%. So your confidence level in this case, you take that 0.0398 number, you multiply it by 2, you multiply it by 100%. What you end up getting is 7.96%. Okay, 2 times 0.0398 times 100% gives you this number here. This is your confidence level. So this is the number that you need to answer the question in this comparison. Compare the accelerations. Okay, so here you would essentially write something like we can be confident to, or we can have a confidence level of, and you might say something like only 7.96% that there is a measured or measurable difference in acceleration between the half length and the full length. And you'd say something like that. You don't have to type it exactly how I said it. The basic thing here is that's a very small confidence level. That means that the ranges for these two accelerations overlap quite a bit. It does not mean that we conclude that they have the same value, or that we conclude to whatever 92.04% or whatever, that they are the same. It doesn't mean that at all. It only means that we can only say with about a little less than an 8% level of confidence that there exists a difference. Okay, so that's not a very big confidence level. It basically means that within the margin of error imposed by the precision of the measurements that we've been making, we can't tell that there is a difference between these two, at least not with any substantial confidence. Okay, and so the follow-up question might be, what's the ratio between these between these two accelerations? And 0.15 over 0.148 is very nearly 1. So we'd say that basically we're concluding that they have the same acceleration, within the margin of error for this experiment and so on. At least we cannot tell that there is a difference, and the ratio is approximately 1. You'll find down here that the ratio is not always approximately 1. It might be approximately 2 or 4 or what have you. And you'll find that there is not always a low level of confidence that there is a difference. Sometimes there's a very high level of confidence that there's a difference. Okay, so basically at this point you'd be repeating these steps for this set of data, or these sets of data, I should say. You'll need to write down your masses. I'm not going to do that. You're capable of measuring mass without my having to show you how to do that. And then the last thing that you're supposed to do is write a conclusion based on what you found, based on your data and based on the answer to all these, and then suggest further experiments to extend these findings. Now, there's a lot of things that you could consider here. I do not want to give the answer away because this is part of your grade as well, but because you maybe don't have a lot of experience doing this kind of thing, I'll give you some hints. You might look at, there's a few things you could look at. You might look at some of the equations that we reference above that we don't really test. If you look up here, there's all your statistics equations. We pretty much use everything in here. There's also all these equations in the kinematics part of the theory. One of the equations we don't really end up using in this lab. We use it only obliquely, and we test it only obliquely using one data point, so you might consider, can we extend that? What would it look like to more thoroughly measure that relationship? Another thing that you might look at is that we didn't really make any graphs in this lab. We didn't actually graph any data. Many of the things that we have done here could have had a different experiment that required a graph. We decided to turn this into more of a statistics experiment than a graphing experiment. So you might ask, what would this look like as a graphing experiment? And what would you have to do different to do that? There's other stuff as well. For example, we've taken it for granted that the acceleration has to do with the geometry of your object. Is that true? How would you test that? If you choose to go down that path, you need to be specific about how you'd test that, by the way. You can't just say, oh, I would test the geometry. Give me an experiment that tests the geometry. Describe what that experiment might look like. Okay, so at this point, I've given you everything you need to do, everything you need to know in order to do this lab, both the experiment part and the computation and discussion part. Some of you may have some further questions, and if that's the case, then you are, of course, always free to contact me with your further questions. I'll do my best to answer them. Otherwise, good luck to all of you. And really, I hope you enjoyed this lab. I hope some of you enjoy it. But good luck to all of you in any case. And that's all for today.